All right, so now we move into Unit 4, which is the beginning of radicals. And we're going to start off by introducing some key terminology that we're going to deal with throughout the unit. And then we'll move forward into some practice problems that may be a good reminder of Math 10C or previous radicals that you would have focused on. Now, radicals can be expressed in two different forms. One expression of the radical can either be as a mixed radical, the other can be the entire. Now, we know mixed radicals will have some sort of outside number and some sort of inside number, which we call the radicand. And for a couple examples, you can see in the case of, let's say, negative 2 root 5 or even 5 cube root b squared c, you see that there is a mixture of an outside term, which is called our coefficient, and an inside term, which we call the radicand. Now, we can also see them as entire radicals where everything is underneath the radicals. So whether it's a cube root, a square root, whatever it might be, you could even have a fourth root or a fifth root, we see that everything is in the radicand position. And yes, there could be a negative in the coefficient, but generally we see it as a 1 or a negative 1, and everything is underneath the radical in the radicand position. Now, breaking this down, and we'll highlight that as well in our notes, what we want to do is we just want to specifically look at some terminology revolving around radicals, and it's the following. Again, we have a coefficient value, which is the number out front. We have an index, which is located at the front of the radical, and this is the little number that kind of sits here. And if it's a square root, we typically don't see this. So if it's a square root, we would just write it as the radical symbol without an index there. If it's a 3 or a 4 or a 5, we'll definitely have some sort of visible index there. The radical sign is just the sign itself that houses the overall radical. And then the radicand is everything that exists underneath the radical sign. And all together, all of these pieces make up a radical. All right, now going down, what is a like radical? Like radicals are things that share the same index and the same radicand. So if we look at the following examples here, there's two key details we want to pull out that are the same. The first is that if we look at this, and I'm just going to highlight the first piece, we have a 3 and a 3 in the index spot. Because they're both cube roots, we would say that they're similar roots. The other piece that would make this a like radical is having the radicands that are same. If those two elements are the same, we can say that these are like radicals. Similarly, if I go over to this example here, well, I see that they're both square roots, and square roots are symbolized with no number written in the radical symbol here. So we just see an empty position, but technically it's the square root, or it's 2. We also see that they both have BC under the radical in the radical radicand position, and so therefore they are like radicals because they're both square roots and they both share the same radicand. Okay, now going down to radicals that can be added or subtracted, we can only add or subtract radicals such that they have like radicals. If they don't have like radicals like the examples above, then we cannot put them together. Another thing we want to recall is the multiplication property, where if we multiply radicals or if we multiply terms under a radical, they can actually be separated into their own radical. Similarly, what I can do is I can go the nth root, and I'm just going to increase the size of that there. So this is the nth root of, I can write a divided by b, and this is the same as saying the nth root of a divided by the nth root of b. Exact same concept here follows for division. You can separate them into their own radicals. As long as they're being multiplied or divided, this property holds. And then again, where n is some sort of natural number, because we can't have a negative radical. That wouldn't make sense here. Okay, now something very, very important we want to highlight here is radicals that are in their simplest form occur when the radicand does not contain a fraction or some sort of fractional value or any factor which can be removed. So we don't want to have any sort of perfect square that could technically be removed, or a perfect cube that could be removed, or even a higher radical. The other piece is we want the denominator to not contain a radical. That's very, very important. We don't have a denominator that includes a radical. In fact, what we're going to call that when we get rid of the radical in the denominator is we're going to rationalize them. Now, some examples of radicals not in simplest form are things like root 18, 2 over root 3, we have 2 square root 7 over 9. The issues with all of these is, first and foremost, I can simplify this by taking a number out from 18 and then perfect squaring it. This one, there's a radical in the denominator, which we don't like. And then the other case, or our third case, we have a fraction on the radical, and we don't want fractions there. So we'll see very shortly how to deal with all three of these, but just know all three of these are examples of things that would be not in the simplest form that we're looking for. Now, restrictions of the variables or restrictions on the variables in the Radican, we need to identify what numbers will make the overall expressions real. It's really important that we take a look at it and we restrict it to values that will only make it real, because if we have certain values, we're going to notice that it actually will make these radicals not real. And if they're not real, then we don't want to consider them, at least for now. So first and foremost, our denominators cannot be zero. And we know that from previous grades, we know that from other units. Our denominators cannot be equal to zero, because if they're equal to zero, this is an undefined solution. The other piece that we have is if the index is even, such as a square root or a fourth root or a sixth root, we must have a radican that is not negative. So if I have something like this, where it's square root of -1, this is actually I. Square root of -1 is I, and you're going to learn that maybe down the road if you pursue STEM. And I is an imaginary number. It's part of the complex number field. We don't want to consider these. Similarly, we don't want to take the fourth root of a -3. These are both considered to be not real. So it's very, very important, or non-real solutions. If the index is odd, however, we can have any number be in the Radican position, because even if we take a negative or a positive, negatives and positives for things that have an index of 3, 5, 7, any of the odd numbers, these are all considered to be real numbers. So be very careful. We don't want to divide by zero. We also don't want to take the square root or an even root of some sort of negative value. Okay, moving forward, let's look at the restrictions first and foremost and how these should be observed. So let's say I have the example A. I take the square root of x minus 2. Well, we know that the Radican position, or the piece that's here, must be greater than or equal to 0. If this is 0, that's fine. We can square root 0, but it can't be a negative number. Therefore, what I'm going to say is that my x minus 2 must be greater than or equal to 0. If I algebraically isolate this such that I get my x alone, I'm going to end up finding that as long as x is greater than or equal to 2, we can therefore say that this will satisfy the inequality and we're not going to get a non-real number. Okay, for my next one, as long as x and y are greater than or equal to 0, then this radical will work. Meaning, as long as x is greater than 0 and y is greater than or equal to 0, both of these, as long as they're greater than or equal to 0, we're fine, because we can definitely have 0 under the radical, we just can't have a negative under a square root. Now, moving on to our next example, we notice that we have an index of 3. If the index is 3, or that we see that it is odd, then there is no restriction, because this doesn't have to be negative or positive or even 0. It can be any of those, so therefore we just simply say no restriction. There is no value of x that would cause this to conflict. Okay. Lastly, we see this situation. Well, we know that we can't have a denominator equal to 0, so let's just make a note about that right away. Denominator cannot equal 0. So unlike our first examples, where if we shuffle back here, they could equal 0. They could equal 0 because they were in the numerator. For this situation, it cannot equal 0. So now what we're going to have to do is take the piece under the radical, 3x or 3 minus x. This must be strictly greater than 0 because it cannot equal 0 in the denominator. And now if we isolate this, we're going to add x across just to make x positive. This is going to give us that x is less than 3. And that's just me flipping the inequality. I could write it in the way that we added across. So if I wanted to go 3 is greater than x, we could also write this and say, or x must be less than 3. Perfect. Okay, so restrictions are very important because we need to know what values of x will be eliminated, or what values of x we should consider such that these things stay as real answers. Because the minute they become imaginary solutions or they become non-real solutions, that means that we're doing something wrong, especially in our pre-calculus courses. Okay, convert each mixed radical to entire radicals. This is a skill we did in Math 10C or previous grades, even Math 15. We can look at this and say, well, in order to convert this into an entire radical from a mixed factor, we need to take this and raise it to the index. So if this is an index of 2 because it's a square root, I'm going to take the number from the outside, which is the coefficient, and raise it to the index. This means that this is going to become the square root of 9 times 5. Well, 9 times 5 is going to end up giving us the square root of 45. So now that we have everything entirely under the radical, we're good. Okay, we go to B. B, instead of it being a square root, it's a cube root. So I'm going to make sure I write the cube for the index, and then I'm going to put my radical symbol. I'm going to raise 2 to the power of 3 instead of 2 to the power of 2. This is going to give me the cube root of 2 cubed in your calculator or even mentally is 8. 8 times 5, this is going to give us that the cube root of 8 times 5 is cube root of 40. Perfect. Okay, so we see the pattern that if we bring a number back underneath the radical, we raise it to the power of whatever the index is. Let's do the same thing for this one. So if I want to bring everything underneath the square root, I have to raise the a to a 2, I have to raise the b to a 2, and then set it multiplied to the c that was already existing there. Lastly, if I want to take this example, well, I have a 5 and a b outside of a cube root. To bring them underneath the cube root, I'm going to write it as 5 cubed times b cubed, because I want to cube both the things I'm bringing underneath. There was already a 3b squared underneath. This is going to give us the cube root of 5 cubed in your calculator or even mentally is 5 times 5 times 5, which is 125. B3 times b squared, we know from our Math 10C, if you have a common base, such as b3 and b squared, you multiply them together, you add their exponents, so it's going to be times 3, which was there, and b5. Last thing I'm going to do is just multiply the 125 by the 3. 125 by 3 is equal to 375, and this will become b5 there. Perfect. So we don't want to have them all just as sporadic b's and a's and all this other stuff or sporadic variables. We want to collect all our terms together in terms of numeric coefficients. We also want to combine all our variable exponents. Okay. Now, as a reminder, we have the laws of exponents and fractional exponents. Starting off with the laws of exponents, we know, again, like in that previous example, if I multiply common bases, I can add their exponents. If I divide them, I'm going to subtract their exponents. Last two, if I have some sort of x or some sort of base of y, and they're raised to a power, but there's another power outside, we're going to multiply this power by the power outside. We're going to multiply our n power by the power outside, therefore giving us this. Now, for anything that's raised to a 0, we always know it's equal to 1, and our only restriction is that the base is not equal to 0 itself. As long as this is any number but 0, then we will get 1 as our solution. Lastly, if we go into our fractional exponents, it's really important to see that a square root is technically written as x to the 1/2. A cube root is x to the 1/3. And then for any sort of other root, we can always write it where the power is in the numerator and the index is in the denominator of the fractional exponent, or as we call them, rational exponents. Okay, now let's go down and we're going to go in the reverse direction. What if we have an entire radical and we want to make it a mixed radical? Here's what I'm going to recommend you do. I'm going to recommend that in your calculator, you type in y1 is equal to x squared, and in y2, I would like you to type in x cubed. Now, what this is going to allow us to do is once you've typed these in, I then want you to go second table if you have the TI calculators, or the blue button and the fourth button on the top, second table. In the Casios, I want you to click menu and table once you've entered these into your graph mode. And what this is going to show you is the perfect squares and perfect cube tables of the numbers. Now, this will take you numbers 1 through infinity in terms of the x's, and it will give you the squares and the cubes of those numbers. What we're going to do is use that table to assist us and say, well, if I take 200 and I divide it by the largest perfect square possible, 100 will divide into 102 in this way, or 200 will divide into 102. I can then go, well, if they're on one radical multiplied, I can separate them into their own radicals as 100 square rooted and then the square root of 2. 100 square rooted is 10. The square root of 2 is irrational, so I keep it exactly as this. There's my answer. Now, similarly, I can do the same thing with cube roots. I'm going to write this as the negative cube root of 250. If I choose the largest perfect cube to divide it by is 125 and 2, this is going to end up giving me negative cube root of 125 times the cube root of 2, because we can separate the pieces of the radicand if they're multiplied. Then we can say this is equal to negative the cube root of 125 is 5. The cube root of 2 is irrational, so we're going to keep it in this form. Okay, let's do a couple more examples on the next page here. We look at square root of 48 with a4b3. We have to do a bit of a trick here. What we're going to do is we know that the index in this position, and if we need to point it out here, maybe we'll do this. The index here is equal to 2. So the index is 2, and if the index is 2, we want everything to be square rootable that we can remove. I'm going to go to our square root table, or just mentally think about the largest possible square root here. It would split apart into 16 times 3, which is 16 times 3 is 48. Now, I'm going to make sure that all my powers on the variables can be divided by 2. A4 can definitely be divided by 2. I'm going to split b into b2 times b1. When I split it like this, what this allows me to do is divide by the index. So square root of 16 is 4. Square root of a4, we divide 4 by 2, or whatever the index is, this becomes a squared. Then we do the same thing for b. B divided, or the 2 divided by 2 in the exponent will become b1 on the outside. Now we square root and leave behind everything that was unsquare rootable or that would be irrational. So square root of 3 times the b1. Done. We leave behind anything that does not divide evenly in terms of divide as an exponent or that cannot perfect square as a value. Okay, now we're going to go over to our second example. Same kind of idea. We're going to split 63 and a and b into certain values here. So 63 can split into 9 times 7, 9 being the perfect square, 7 being irrational. I can then take a7 and split it into a6 times a1 as a way to have a perfect square for an a. And then I can take b4, because 4 is divisible by 2, we're going to leave it as is. Now, I'm going to take the square root of 9, which is 3. The square root of a6 is dividing this by 2, which becomes a3 on the front. I'm going to divide b4 by 2, which is then going to give me b2 out front. Lastly, I leave behind the things that would be irrational. 7 and the singular a are left behind. There's your solution. Now, if I wanted to undo either one of these problems, like let's say I wanted to get back to the original position, what I would do is take the coefficient term here and here, and then I would square the entire thing to bring it back underneath the radical. And if you want to try that out, go for it. But I feel pretty confident in these given solutions here. Now, what we're going to do in our next example is we're going to compare and order radicals without using a calculator. This is actually easier than we may think. Now, it does require a little bit of mental math in this case and just kind of thinking on the spot here, but we're going to use just general algebra and our estimation strategies in order to rank these. So starting off with the first one, if I take a square root that's less than 300, a perfect square less than 300 is 289, which is less than the square root of 300, which is less than the square root of 324. Now, the square root of 289 is 17, which is less than the square root of 300, which we're trying to figure out, which is less than 324 square rooted, which is 18. Now, you want to be like, which is it closer to? Is 300 closer to 324 or 289? It's a little closer to 289. So what we're going to do is we're going to say the square root of 300 is approximately equal to the 17 point, and we could do like 3 or 4. I'm going to say for this one, maybe like 17.3, just because it's a little closer to 289 than 284. Okay, we're going to move on to our next one. In order to solve this next one, what I'm going to do is a very similar strategy that we just did, but I'm going to do a bit of a precursor step here. I'm going to take the outside coefficient of 3 over 10 and bring it under the radical and simplify. This will end up giving us the following. The square root of 3 squared is 9, 10 squared is 100, multiplied by what's already existing underneath there. This will then simplify to, if we multiply this out and divide by 100, we get 315. And the nice thing is we actually get a very similar setup to our last one. We're going to take the square root of 289, which is less than the square root of 315, which is then less than the square root of 324. There we go. And let me redo that radical there. So 324. Excellent. Now from here, we're going to get that 17 is less than the square root of 315, which is less than 18. Now from here, we're like, okay, which one was 315 closer to? Is 315 closer to 289 or 324? It's definitely closer to this side. So we're going to say that roughly that 315 is approximately equal to something like 17 point, maybe even like 7. And again, we're doing general estimation here. So because we're not doing these with a calculator, we just need to kind of approximate this decimal, where if it's a little bit closer to this side, we're going to make the decimal a little closer to 18 than 17 flat. Okay, our third option was 18. 18 is just 18, so there's nothing we can do with this radical wise. Lastly, what I'm going to do is I'm going to go over here before we start ranking these, and I need to figure out this one. Well, let's see if we can write this in a different way. Rather than bringing the 9 under the radical, what I'm going to do is write it as 9 square root of 15 over square root of 4. We know if they're being divided, we can separate them. This will then end up giving us 9 over 2 square root 15. The reason it's 9 over 2 is because the square root of 4 is simply just 2. Now what we're going to do is use our estimation strategy and say, well, 9 over 2 with the square root of something that's less than 15, that's a perfect square, which is 9, is less than 9 over 2, which is the square root of 15, which then we are going to say that the is less than 9 over 2 times the square root of 16, which is the square root above. Now let's simplify this a bit. It's going to be 9 times 3 over 2 is less than 9 over 2 square root 15, which we don't know, which is less than 9 over 2 times 4. As values, 9 times 3 is 27. 27 over 2 is 13.5, which is less than 9 over 2 square root 15, which is then less than 9 times 4, which is 36. 36 over 2 is 18. So we're going to approximate this to be 9 over 2 square root 15 is approximately equal to, well, we see that 15 is a heck of a lot closer to 16 than it is to 9. So I'm going to make this something like 17 point, let's make it like even 8. 17.8 or 9 would be fine. Now, you can make this a little bit higher, you can make it a little bit lower, but that would be okay. Now, actually, I think if we compare these, this one seemed a little bit closer. So we had 17.7. This one is pretty close. We could say like something like even 17.6 here. I'm gonna throw out that guess. That's 17.6, and then I'm gonna make this one 7.7, and then this one 7.3. And again, these are all approximations with the numbers like this. That's all we can really do is say it's gonna be roughly a little bit closer to one side than the other. And in this case, because it's 15 being close to 16, and then the other one was 315 is closer to 324, there's a closer gap technically here between these two than there is from these two to these two. It's a little bit theoretical, but yes, we're going to see this as, let's say it's 17.6. Now, I could be totally wrong again because we're not using a calculator, but this is a rough approximation. Okay, now we're going to rank them all out in ascending order or first to the highest. So therefore, and let's see if I have room below. No, I don't. So I'm going to do it above here. Therefore, in ascending order, our lowest value was the square root of 300. We're going to use the original values. The next one, we have 7.7 or we have 7.6. We're going to put the 9 over 2 square root of 15 as the second value because this one ended up being a little bit less. We can then say our square root of 3 over 10, all square root of 3,500 was third because this one was our 7.7 approximately. And then lastly, we have 18, which was just the whole number. Now, what I want to do is just for the sake of it, I actually want to pull these up on the calculator and just see if we got close or maybe if we made a mistake in the estimations because they said without a calculator or without technology do this. We did it without technology. Let's see if we can actually just compare and see for those certain values here. So I'm going to go to my calculator here and I'll pull it up from my notes here. So let's bring this one here. Perfect. Okay, we're going to clear that out. Now, if I take the alpha y equals and I go 9 over 2 times the square root of 15, this is equal to 17.4. So for this one that's on the very end, we should have got something like 17.4. Approximately, we got 17.6. That's not actually a bad guess for not using technology. So this should have been 17.4, but we end up getting 17.6. I'm okay with that. The other one we want to test is our square root of 315. Our square root of 315 is equal to 17.7. Hey, look, we're right on the dot with that one. So we actually didn't do half bad. The other one we want to check is the square root of 300, which is 17.3. Hey, we got it right on the nose. So just even using approximation, we can get pretty close, but we can also get slightly off, which is totally fine here. At the end of the day, that is okay. If we're off just by a little bit, I'm generally okay with that. So 17.4, 17.7, 17.3 looks like our rankings are fairly decent here. Okay, and then in ascending order, just make sure that you highlight that piece in your notes because we want to have it from least to greatest. Okay, now let's move on to adding and subtracting radicals. This one section should go quite quickly now that we have the ability to go backwards and forwards between entire radicals and mixed radicals. Let's say we're dealing with this one. Well, two things we need to look at before we add them. Are the indexes the same, which they are? are the radicants the same, which they are. If that's true, we're going to go 2 plus 13, which is 15, root 7. There's our answer when we combine it. What about b? We see that we have the indexes that are both square roots, but if they're both square roots, but the radicants are different, we need to do some work with this. I'm going to take 24 and separate it into 4 times 6 minus the square root of 6. This is going to give us 2 root 6 minus 6. And if you're unaware of what the coefficient of this term is out front here, this is actually equal to 1, or more importantly, negative 1. So we're going to go 2 minus 1 root 6. We subtract their coefficients, I get 1 root 6, which is just going to be written as root 6. All right, we go down to our next example. We see cube roots, square roots. We're going to have to do some work with these. I'm going to write the first one, 4 cube root. I'm going to split 54 into, let's see if we can do maybe 27 and 2. So 27 times 2 plus, I'm going to split 50 into 25 and 2, because we're trying to split them into cubes and squares that work. I'm going to go minus 5 times 18 can be split into 9 and 2 with a perfect square and a non-perfect square. And then for the last one, the cube root of 16, I can write this as maybe 8 and 2. Okay, now I'm going to move this over just a tad because I don't want to interrupting our second equation there, or our second one there. Perfect. Okay, now we're going to go one by one down and simplify. This will be 4 times the cube root of 27, which is 3, cube root of 2, plus square root of 25 is 5. We leave behind the irrational component of 2, minus 5 times the 3, which is the square root of 9, leave behind the irrational square root 2. Lastly, plus the cube root of 8 is 2. We leave behind the cube root of 2, which is the irrational component. Now, we're just going to do one more step here before we simplify. We're going to go 4 times 3 is 12, cube root of 2, plus 5 root 2, which nothing we can do there. Negative 5 times 3 is negative 15, square root 2. And then lastly, we have plus 2 cube root 2. Now, we want to organize them by what are the like terms. Well, if we see the cube roots and they both have a cube root and a radical with a radicand of 2, these are like terms. Our other like terms are our squared terms that include not only an index of 2, but a radicand of 2. So if we see those things, we can add or subtract these. We're going to go 12 plus 2 cube root is 14 cube root of 2. Our 5 minus 15 is negative 10 square root of 2. So just as you're looking at this, when we're adding and subtracting radicals, we do not change the index that's happening. We don't change the radicand. We only change the coefficients. So there's our final answer. Okay, now we go over to this one. It includes some variables. Don't sweat it, no problem. Very, very similar solution. We're going to split it up into a perfect square and an irrational number. This is going to make this 4 times 5x minus 3 times 45 can split into 9 and 5x. We're going to take out the square root. Square root of 4 is 2, leaving us with 5x minus 3 times 3, which is the square root of 9, times 5x. From here, we're going to then write this as 2 square root 5x minus 3 times 3, which is 9 square root 5x. And one thing we need to look for is, are our indexes the same? They are. Are our radicands the same? They are. So therefore, we can take our coefficients and subtract them. 2 minus 9 is negative 7 square root of 5x. Again, when we're adding and subtracting, we do not change the radical or the radicand or the index. All we change is the coefficient. Okay, let's do a couple more problems on this. So let's say I give you this problem here. Well, what do we notice? We see that there's an 8, 18, and 3. They can't be added as is. So we're going to alter this and go 5 times 4 times 2 under the radical minus 3. We're going to write this as 9 times 2. And then for our last one, we can't really do anything with this, so we're going to keep it as is. I'm going to simplify this as 5 times 2 square root 2 minus 3 times 3 square root 2, and then plus 2 square root of 3. From here, this is going to become 10 square root 2 minus 9 square root 2 plus 2 square root 3. Now we realize that in this term, these two are common. Our 2 square root 3 is not common to either one. So now I'm going to say it's 10 minus 9, which is 1 root 2, and then plus 2 root 3. If the radicands are not the same, such as 2 and 3, we just have to leave our answer as this. It's done. Okay, We then go to one with a bunch of variables. If we look at the one with a bunch of variables, which is part F, very, very similar. We're going to look at this and say, well, 4 is going to stay on the outside, cube root of. In the inside, we know that 8 is actually a perfect cube. So I'm going to keep it as is. This will be 8. In terms of the x, I can't really do anything with that because no matter how much I split up x, it won't divide by 3. And then y4, I'm going to split this into y3 and y1 because when I split it into that, I can divide one of them by 3 to remove it with the cube root. Minus 2 cube root of x to the 5. I'm going to split this into x3 and x squared so that I can take at least one of the x's out, or one part of the x term. Therefore, this is going to give us the 4 times the cube root of 8, which is 2. The cube root of x squared, that's going to stay behind. Cube root of y3 is going to take out a y. And then the y1 will just stay there. It's going to be cube root of x squared and the y that remained. Okay, we're going to do the second piece here, which is negative 2. The cube root of x cubed, this is 3 divided by 3. 3 divided by 3 is going to remove out 1x. That's all that can come out here, so we leave cube root of x squared and y. So again, when we're dealing with variables, we want to split it such that we can get a variable that is divisible by the index. If it's divisible by the index, then we can remove out a term by cube rooting. Now from here, what we realize is that not only are our x squareds and y's the same as the radican, but our index is the same. If that's true, we can put together our coefficients. This is going to become 8y, the cube root of x squared y, minus 2x, the cube root of x squared y. From here, I'm going to put together those two coefficients, 8y minus 2x, and I'm going to factor out the GCF of the cube root of x squared and y. So if we see that this term is the same for both of them, which in this case we have an x squared y that are both being cube rooted, that can be factored out as a GCF, and we pair together the outside terms in one binomial here. Okay, let's look at a couple applications before we wrap up the lesson. So adding and subtracting in terms of perimeter. So let's say I was given this and we want to determine the exact perimeter. Exact perimeter is just a fancy way of saying, can we put these together in a simplified mixed radical? Now to do this, I'm going to write this as equal to, I split it into 4 times 3, which will then become 2 square root 3 meters as a mixed radical. For my 27, I'm going to split this into 9 times 3. We know the square root of 9 is 3, so this gives me 3 root 3 meters for the perimeter value for specifically this piece from A to C. Now we want to put these all together. So we're going to add AB, BC, and AC all together. Off to the side, let's do that. Therefore, the perimeter is equal to the square root of 3 plus 2 square root 3 plus 3 square root 3. This is going to give us a perimeter value equal to, we know the coefficient on this one is 1, 1, 2, and 3 all add up to make 6 square root 3, and we're going to throw the meters on that because that will be our final answer, and we want to have units when it's an application problem. Okay, last question here is example 7. We have a square that's inscribed in a circle. Inscribed is just a fancy way of saying it's overlays within the circle, and we have the area of this overall circle is 38 pi meters squared. What is the exact length of the diagonal of the square? So let's label a couple things here. If we know that we're looking for the diagonal, this is what they're looking for here. Now, we know that the diagonal stretches from one side to the other. If we only go from the halfway point, meaning the middle, to the edge or to the perimeter, this is going to be the radius. So we can actually use the fact that we know we have area, which involves radius, to then help us get diameter. So what I'm going to do is in part A here, let's actually break this down and say, well, we know area of the circle is equal to pi r squared. Area of the circle was given as 38 pi, which is equal to pi r squared. We're going to isolate for r by dividing by pi. When we divide both sides by pi, we end up getting that 38 is equal to r squared. Now what we're going to do is take the square root of both sides, and we're going to end up finding that r is equal to the square root of 38, and this is in meters. Perfect. So this is the exact value. When they say exact length, we don't want to put it as a decimal. I know it's tempting, but we're going to leave it as this. This is our radius. Now we want to figure out the diagonal. In order to get the diagonal or the diameter, this is equal to 2 times the radius. Therefore, the diagonal or diameter is 2 times the square root of 38 meters. And we're just going to keep it exactly as that. Perfect. Okay, so we have our diagonal, we have our radius. Now what they want us to figure out in part B is determine the perimeter of the square. To determine the perimeter of the square, we need the outside lengths all added together. So length plus length plus length. We know on a square they're going to be all the same. So we just need one of them, and then we'll multiply it by 4. In order to do this, we can use Pythag because it's a triangle. We have a right triangle given by length, length, and the hypotenuse of diameter. So I'm going to use Pythag theorem right away and say that our diameter squared is equal to the radius squared plus, or not the radius, but the length squared plus the length squared. This means that our diameter, which is 2 square root of 38, all squared, is equal to, on the right-hand side, there is 2 length squareds, because they're the same value. Now what we're going to do is we're going to expand this by applying the exponent into both brackets here. This is going to give us 2 squared is 4. The square of, or the square root multiplied, or to raise to the power of 2, just gives us 38. And if you're unsure about this rule being applied here, what we're doing is we know that if I have, and you may want to note this off to the side, so I'll even put like note. If I take the square root of some number, let's call it x in this case, and I'll just clean this up a little bit. If I take the square root of x and I raise it to the 2 power, we know that a square root and a square are opposite operations. Therefore, this is simply just going to be equal to whatever the radicand is. In this case, that's 38. Now from here, we're going to end up multiplying this out, or dividing by 2, I think might be the more sensible option. When we divide both sides by 2, we end up getting that length squared is equal to 2 times the 38. And then what we're going to do is we're going to square root both sides. Now, just to see if we get an exact value here, this means that we get length squared is equal to 70, in this case 76, because 38 times 2. We're going to square root both sides, square root the length, square root the length. Carrying this forward up here, maybe we'll just do this off on the right-hand side. We end up getting that we get a length is the square root of 76. Of course, we don't want to keep this as an entire radical because most simplified is a mixed radical. I'm going to split this into 4 times 19. 19 is a prime number, so I know I chose the right thing. Each length is going to be 2 square root 19 meters, and therefore the total perimeter is going to be equal to 4 times the lengths, which is equal to 4 times 2 root 19, which means that the overall perimeter is equal to 8 root 19 meters. Now, it's very, very important that we're not multiplying underneath the radicand. So there'll be a time and place, including next lesson, where we're going to multiply radicals together, and that will affect the radicand. But in the case of this, if you just take a coefficient number and you multiply it to a coefficient with a radicand or a radical, you just simply multiply the coefficient values together and make it 8, and you leave this alone. Unless there's another radical, then we would adjust it. But otherwise, this is our overall perimeter. All right, here's where you want to move on to the assignment. So try and get some practice with these, especially with those earlier things of converting from a mixed radical to an entire or entire to mixed. And you should get some application problems done in terms of, can you add or subtract certain radicals? I think that's going to be really important. And then if you have time, then move on to these more like applied problems like this. All right, good luck with your practice.